The magnitude 6.0 earthquake off Oregon wasn't the story. The story is everything happening around it. High-speed solar wind, geomagnetic storms, a rare planetary configuration, a volcano inflating 7 meters beneath the ocean, and Cascadia, the fault capable of magnitude 9, going absolutely silent. When systems start deviating from baseline simultaneously across multiple domains, patterns emerge that challenge what we thought we understood. This isn't fear-mongering, it's pattern recognition in real time. So settle in, because we're going to walk through why scientists are asking uncomfortable questions about triggers, timing, and whether the localized tremor off the coast of Oregon is just that, or the precursor to a much larger 7.5 plus event during this high-risk window. Subscribe and follow along as more data from Cascadia, axial seamount, and the sun continues streaming in. Because what unfolds over the coming weeks will either confirm that these are random coincidences or reveal dangerous blind spots in how we understand Earth's response to converging stressors. This isn't about predicting the next earthquake. It's about recognizing the pattern that's already unfolding. A magnitude 6.0 earthquake struck off the coast of Oregon at exactly 9:47 a.m. Pacific Time on January 14th, 2026. The shaking lasted 12 seconds. Buildings swayed in Portland. Coffee spilled in Seattle. Emergency alerts lit up phones across the Pacific Northwest. Within 20 minutes, the United States Geological Survey issued a standard assessment. Shallow offshore quake, no tsunami threat, minor damage expected. The news cycle moved on by lunch, but something about this one didn't sit right with the people who watch earthquakes for a living. You see, a 6.0 isn't catastrophic. It's not even particularly rare along the Pacific Ring of Fire. Oregon gets these every few years. The Juan de Fuca Plate grinds beneath North America constantly, releasing tension in manageable bursts. That's the system working as designed. What made this earthquake different wasn't its size. It was when it happened, and what else was happening at the exact same moment. The quake arrived during a convergence that seismologists hate acknowledging in public because it sounds too much like astrology. But the data doesn't care about optics. On January 14th, Earth was being hit by high-speed solar wind streams originating from two massive coronal holes near the sun's equator. These streams had been traveling through space for 3 days, accelerating particles to over 1 million miles per hour. When they reached our planet, they compressed Earth's magnetic field like a fist squeezing a water balloon. At the same moment, the Geomagnetic Activity Index, called KP, had climbed to 6 out of 9. That's the threshold where auroras start appearing in places they shouldn't, where satellites begin experiencing interference, where power grids start reporting anomalies. The global electric circuit, that invisible web of electromagnetic potential that connects Earth's surface to the ionosphere, was charged up like a capacitor holding more voltage than usual. And there's one more thing. On January 14th, Mercury, Venus, Earth, Mars, and Jupiter formed what astronomers call a heliocentric alignment. Not a perfect straight line through space, that almost never happens, but close enough that their combined gravitational influences on the sun create measurable tidal effects on the solar plasma itself. This doesn't pull on Earth's crust directly. Planetary gravity at these distances is trivial compared to the moon's tidal force, but it does affect solar activity patterns in ways we're still mapping. So here's what we had: a significant earthquake, elevated solar wind, heightened geomagnetic activity, and a rare planetary configuration, all stacked on top of each other within a 12-hour window. Coincidence? Probably. Almost certainly. The smart money is always on coincidence. But when you work in seismology or space weather, you learn to track coincidences anyway. Because every once in a while, timing matters more than cause. Every once in a while, multiple small stressors arrive at the same instant that a fault system is already loaded to its breaking point. you get what researchers privately call a timing stack, where unrelated factors peak together and create conditions that wouldn't exist in isolation. The public statements came quickly. The National Oceanic and Atmospheric Administration said the geomagnetic activity was expected and routine. The USGS said the earthquake was consistent with normal tectonic activity in the region. NASA's Solar Dynamics Observatory noted the coronal holes, but emphasized they pose no danger to Earth. Everything was fine. Nothing unusual to report. Behind the scenes, instrumentation networks went into elevated monitoring mode. Seismometer arrays along the Cascadia subduction zone increased their sampling rates. Magnetometer stations began filing more frequent reports. Research institutions quietly updated their internal risk assessments, not because anything had changed officially, but because when the data gets weird, you pay closer attention. The question scientists were asking themselves, but not saying out loud, was simple. Did this earthquake release stress, or did it move stress somewhere else? You see, a magnitude 6.0 sounds significant, and it is. But in the context of plate tectonics, it's a medium-sized event. It releases energy equivalent to about 15,000 tons of TNT. That's nothing compared to what the Cascadia subduction zone is capable of storing. The last time Cascadia fully ruptured, in 1700, it released energy equivalent to several million tons of TNT across a rupture zone stretching from Northern California to Vancouver Island. That was a magnitude 9.0. So when a 6 happens, the immediate question isn't just what broke. It's what didn't break. What parts of the fault system absorbed that shock and held. Because sometimes, a medium earthquake doesn't relieve pressure. Sometimes it redistributes pressure. Sometimes it locks adjacent fault segments even tighter than before. And that's when scientists start watching the silence. Because Cascadia has been quiet. Very quiet. Uncomfortably quiet. And after January 14th, it got even quieter. The Cascadia subduction zone runs for 700 miles along the Pacific Northwest coast, from Cape Mendocino in California to Vancouver Island in British Columbia. It's where the Juan de Fuca plate slides beneath the North American plate at a rate of about 1.5 inches per year. That might not sound like much, but over centuries, it adds up to dozens of feet of accumulated strain. When that strain releases all at once, you get earthquakes that rewrite coastlines and generate tsunamis that cross oceans. The last full rupture happened on January 26th, 1700. We know the exact date because Japanese historical records documented a tsunami that arrived with no preceding earthquake in Japan, meaning it came from across the Pacific. Scientists worked backward from those records and matched them to Native American oral histories and geological evidence of sudden coastal subsidence. The earthquake was so powerful that it dropped beaches by several feet in a matter of minutes and sent a tsunami to Japan 9 hours later. That was 326 years ago. The average interval between full Cascadia ruptures, based on geological evidence, is somewhere between 300 and 600 years, which means we're either overdue or we're not, depending on where you are in the probability distribution. Statistics are comforting until you realize they don't predict specific events. What scientists look for instead are patterns, changes in baseline activity, deviations from normal behavior. And right now, Cascadia's behavior is deviating in a direction that makes people nervous. After a magnitude 6.0 offshore earthquake, you'd expect to see increased microseismic activity along the fault zone. Small aftershocks, stress redistribution events, tremor migration as the crust adjusts to the new configuration. It's like watching ripples spread across a pond after you drop a stone. The ripples tell you how the water is moving, how energy is dissipating, how the system is returning to equilibrium. But the ripples aren't there. Cascadia went quieter after January 14th. Seismometer networks that normally register dozens of tiny tremors per day started showing cleaner signals, fewer background events, less noise, It's like the fault zone is holding its breath. This phenomenon is called stress shadowing, and it's one of the more unsettling observations in seismology. When a fault segment ruptures, it doesn't just release stress in that immediate area. It transfers stress to adjacent segments. Think of it like pressing down on one section of a mattress. The area under your hand compresses, but the areas around it bulge upward. The total stress hasn't disappeared. It's just moved. A magnitude 6.0 earthquake off the coast of Oregon released stress in that specific patch of the subduction zone, but it may have simultaneously increased stress in the segments to the north and south. And one of the signatures of increased stress is decreased small-scale activity. The fault gets locked tighter. Friction increases. Small slippages that would normally occur get suppressed. The system stores energy instead of releasing it. Geophysicists call this the quiet before the storm, but they hate the phrase because it sounds too dramatic. It implies prediction, and earthquake prediction is still impossible. What they can say is that large earthquakes are often preceded by periods of reduced seismicity in the rupture zone. Not always, not predictably, but often enough that it's a recognized pattern. What else isn't happening is slow slip events. These are fascinating phenomena where sections of a fault creep forward very slowly over days or weeks, releasing stress without generating felt earthquakes. Cascadia experiences slow slip events regularly, particularly beneath the Olympic Peninsula in Washington and Vancouver Island in British Columbia. They happen roughly every 14 months and are accompanied by increased tremor activity as the plates slide past each other in slow motion. The last major slow slip event was in September of 2025. The next one should be starting right about now, in January of 2026. But the instrumentation networks aren't detecting the characteristic signals. No slow slip, no tremor migration, no subtle GPS displacements indicating the plates are creeping. Just silence. Historical records show that this kind of calm can persist for months before major earthquakes. The 1964 Alaska earthquake, a magnitude 9.2, was preceded by a 2-year period of reduced seismicity in the rupture zone. The 2004 Sumatra earthquake, a magnitude 9.1, occurred in an area that had been seismically quiet for decades. The 2011 Tohoku earthquake, a magnitude 9.1, ruptured a segment of the Japan Trench that many considered to be locked and accumulating stress. None of this means a major earthquake is imminent on Cascadia. Quiet periods don't predict earthquakes. They're just one more data point in a probabilistic assessment that can never produce certainty. But they do change the conversation among researchers from if to when, and from maybe to keep watching. And there's something else they're watching now. Something most people have never heard of. Something sitting 300 miles offshore in total darkness under 8,000 feet of ocean water. A volcano that might be telling us what the Earth's crust is really feeling. Axial seamount sits at the intersection of obscurity and critical importance. It's a submarine volcano rising nearly 3,000 feet above the Juan de Fuca Ridge, a spreading center where new oceanic crust is being born as tectonic plates pull apart. The summit of Axial is still about 4,500 feet below the ocean surface, which means no one sees it, no tourists visit it, and most people don't know it exists. But it might be one of the most important volcanoes on Earth right now. Axial seamount is the most heavily instrumented submarine volcano in the world. In 2014, the Ocean Observatories Initiative installed a network of seafloor cables, seismometers, pressure sensors, cameras, and fluid samplers directly on the volcano. These instruments transmit data in real time through fiber optic cables to research institutions on shore. Scientists can watch Axial's vital signs 24 hours a day, 7 days a week, with a precision that's impossible for most volcanoes on land. And what those instruments are showing right now is inflation. Volcanic inflation means the ground is rising, swelling upward as magma accumulates in chambers beneath the surface. At axial, ground inflation is measured in meters, not centimeters. The caldera floor, the collapsed crater at the volcano's summit, has risen by approximately 7 meters since the last eruption in 2015. That's over 20 feet of vertical uplift, driven by molten rock pushing upward from below. 7 meters might not sound like a threshold number, but it is. Axial erupted in 1998, 2011, and 2015. Each eruption was preceded by inflation that reached between 4 and 6 meters. After each eruption, the caldera floor dropped back down as magma drained out through fissures on the seafloor. Then the inflation cycle started again. The volcano breathes in, holds, and exhales. Right now, it's holding more breath than it did before any of the previous 3 eruptions. Does this mean axial is about to erupt? Not necessarily. Volcanoes don't follow strict schedules, but the pattern is consistent enough that researchers were already planning for increased monitoring in late 2026. The January 14th earthquake off Oregon added a new variable to that timeline. Here's why axial matters for understanding regional stress. The Juan de Fuca plate is not a rigid slab. It's a dynamic system that bends, flexes, and responds to forces from multiple directions. The plate is spreading at the Juan de Fuca ridge, where axial sits. It's subducting beneath North America at the Cascadia subduction zone. And it's being sheared along the Blanco fracture zone, a massive transform fault that cuts across the plate's southern edge. When stress changes in one part of this system, it propagates through the entire plate. An earthquake on the Blanco fracture zone can affect magma pressure at axial. A slow slip event on Cascadia can trigger seismic swarms at the ridge, and magma pressurization at axial can subtly alter stress fields across the region by changing how the oceanic plate flexes under load. Think of the Juan de Fuca plate as a sheet of metal being pulled, compressed, and bent simultaneously. When you push up from below, at axial, the entire sheet flexes differently. That flexure changes stress distribution at the edges, where the plate is diving beneath the continent. It's not cause and effect in a simple sense. It's coupled behavior in a complex system. Axial seismic swarms have been increasing in frequency over the past 3 months. These are clusters of small earthquakes, magnitude 1 to 3, occurring in bursts as magma moves through fractures in the crust. The swarms don't indicate imminent eruption, but they do indicate active magma transport. The volcano is plumbing itself, opening pathways, redistributing melt. And here's the part that keeps some researchers up at night. On January 15th, 24 hours after the Oregon earthquake, axial experienced a seismic swarm of 63 events in 90 minutes. The swarm wasn't centered in the caldera where they usually occur. It was offset to the northwest, toward the Cascadia subduction zone, along a fracture system that connects the spreading ridge to the subduction zone. Correlation isn't causation. The swarm could be unrelated, but the timing raises questions. Did the earthquake stress transfer through the plate and trigger magma movement at axial? Did the existing magma pressure at axial make the plate more susceptible to rupture during the earthquake? Or are both phenomena responding to a deeper stress field that we don't fully understand yet? Volcanoes don't cause earthquakes on subduction zones, but they can act like pressure gauges for the crust beneath them. When axial inflates, it tells us magma is rising, which means the mantle beneath the Juan de Fuca plate is actively melting and feeding the volcano. That requires heat and decompression. It requires the plate to be pulling apart, thinning, creating space for melt to rise. All of that is happening while the same plate is simultaneously diving beneath North America. The system is dynamic. It's adjusting. And when systems adjust, they sometimes do so in ways that cascade beyond what we expect. Which brings us to the thing scientists hate discussing in public, the variable that makes careers risky and funding difficult, The question that gets dismissed as fringe until enough data accumulates that it can't be ignored anymore. What if forces from above the Earth are influencing when these adjustments happen? Let's be absolutely clear about something up front. There is no proven, widely accepted, peer-reviewed consensus that solar activity causes earthquakes. The gravitational influence of the Sun on Earth's crust is constant and far weaker than the Moon's tidal effects. Solar flares don't crack tectonic plates. Coronal mass ejections don't trigger fault ruptures. Any claim that the Sun directly causes seismic activity is unsupported by current evidence. But here's the harder question, the one that makes geophysicists uncomfortable at conferences. Can solar activity modulate the timing of earthquakes that are already primed to occur? That's a different question entirely. It's not about causation. It's about triggering. It's about whether small perturbations in Earth's electromagnetic environment can act like the final ounce of weight on a scale that's already loaded to its limit. And there's research on this. Not a lot. Not enough to draw firm conclusions, but enough to make the question legitimate. Earth sits inside a global electric circuit. This isn't metaphorical. It's a measurable phenomenon. The ionosphere, that layer of charged particles 60 to 600 miles above the surface, maintains a positive electrical potential relative to the ground. Current flows constantly between the ionosphere and Earth's surface through the atmosphere, driven by thunderstorms that act like batteries, pumping charge upward. The circuit generates a background electric field of about 100 volts per meter at ground level on a clear day. Solar wind changes this circuit. When high-speed particles from the Sun strike Earth's magnetic field, they generate currents in the ionosphere. These ionospheric currents, in turn, induce electric fields at the surface. During geomagnetic storms, ground-level electric fields can spike to several volts per kilometer, which doesn't sound like much until you remember that Earth's crust is shot through with conductive pathways, fault zones filled with mineral-rich fluids, fractures saturated with groundwater, veins of metallic ores. Now here's where it gets interesting. Laboratory experiments on stressed rock samples have shown that changes in external electric fields can influence when the rock fails. Not by much. Not in a way that creates stress where none existed, but in rock samples that are already at 99% of their failure threshold. Small electromagnetic changes can advance or delay the moment of rupture by seconds to minutes. The key word there is already stressed. You can't cause a failure by applying an electric field to unstressed rock. But if the rock is on the edge, if it's loaded to critical stress and waiting for the final perturbation, then yes, electromagnetic changes can potentially act as a trigger. Scale this up to crustal dimensions and you enter speculative territory. Fault zones are not uniform laboratory samples. They're heterogeneous, chaotic systems with stress concentrations, fluid pressures, frictional variations, and geometric complexities we can barely model. The idea that small changes in electromagnetic fields could influence earthquake timing at crustal scales is, at best, a hypothesis with limited supporting evidence. But it's not pseudoscience. It's edge science. There are physicists working on this. There are papers in obscure journals. There are datasets showing weak correlations between geomagnetic activity and seismic event timing. None of it is conclusive. All of it is controversial. And most researchers won't touch it because the risk of being wrong publicly outweighs the benefit of being right eventually. What we can say with confidence is that Earth's electromagnetic environment was unusually active on January 14th. The KP index hit 6. Ionospheric currents were elevated. Ground-level electric fields were higher than baseline, and a significant earthquake occurred during this window. Coincidence? Almost certainly. The odds favor random chance. But the data exists, the timing exists, and the question remains whether we're looking at independent events or coupled phenomena in a system we don't fully understand yet. History is full of ideas that sounded absurd until they became mainstream. Continental drift was ridiculed for decades. The concept of plate tectonics wasn't accepted until the 1960s. The idea that impacts from space have caused mass extinctions was considered fringe until the Chicxulub crater evidence became overwhelming. Science progresses by testing uncomfortable hypotheses, not by dismissing them out of hand. So where does this leave us? It leaves us watching. It leaves us acknowledging that multiple weak influences, none of which are sufficient on their own, might collectively matter when they align during a period of peak crustal stress. Which leads to the question everyone wants answered, but no one can answer. What's the actual risk right now? Is there a window where conditions are more dangerous than usual? And if so, when does it close? The number 7.5 gets thrown around a lot when people talk about Cascadia. It's become shorthand for the big one, the earthquake that would cause serious damage, generate a major tsunami, and fundamentally change life in the Pacific Northwest. But where does that number actually come from? Cascadia is capable of producing magnitude 9.0 earthquakes. We know this because it's done so before, but not every Cascadia earthquake is a full rupture. Sometimes only segments of the fault break. A partial rupture of the southern Cascadia zone from Cape Mendocino to central Oregon could produce a magnitude 7.5 to 8.0 earthquake. That's still massive, still catastrophic in its immediate area, but not the worst case scenario. The distinction matters because earthquake magnitude is logarithmic. A magnitude 8 releases about 30 times more energy than a magnitude 7. A magnitude 9 releases about 1,000 times more energy than a magnitude 7. The difference between a 7.5 and a 9.0 isn't just numerical. It's the difference between a regional disaster and a civilization-altering event. So when people talk about a 7.5 plus window, they're usually referring to the potential for a significant but partial rupture in the near term, not the full-length megathrust, not the repeat of 1700, but something substantial enough to matter. The question is, are we in that window right now? Here's what we know about earthquake patterns. Large earthquakes tend to cluster in time and space. When one segment of a fault system ruptures, it changes stress on adjacent segments. Sometimes those adjacent segments fail hours, days, or months later. The 2012 Indian Ocean earthquakes are a perfect example. A magnitude 8.6 main shock was followed 90 minutes later by a magnitude 8.2 aftershock on a different fault system. The first earthquake triggered the second by transferring stress. The phenomenon isn't rare. The 1992 Landers earthquake in California, a magnitude 7.3, triggered the Big Bear earthquake 3 hours later, 40 miles away. The 2016 Kaikoura earthquake in New Zealand ruptured at least 21 different fault segments in a cascading sequence that lasted over 2 minutes. Each rupture transferred stress to the next segment, creating a domino effect that propagated across the landscape. Cascadia could experience something similar, but on a different timescale. A magnitude 6.0 offshore earthquake might increase stress on adjacent segments. Those segments don't fail immediately because they're not quite at critical stress yet. But they're closer. And if other stressors come along, tidal forces, geomagnetic perturbations, magma pressure changes, the accumulated effect might be enough to tip the balance. This is where probabilistic thinking becomes both essential and frustrating. Seismologists can't say an earthquake will happen on this date. They can only say the probability of an earthquake in this magnitude range during this time window is X%, and X is usually small. Even in elevated risk scenarios, we're talking about probabilities in the single digits over the course of months. But humans are terrible at thinking probabilistically. A 5% chance sounds low until you realize it means 1 in 20. Would you get on a plane if 1 in 20 flights crashed? Of course not. But we accept similar odds in other areas of life without thinking twice. The challenge with earthquakes is that false alarms erode public trust. If scientists raise alarms every time conditions look slightly elevated and nothing happens, people stop listening. But if they stay silent and something does happen, they're accused of not warning anyone. It's an impossible position. The history of earthquake prediction is littered with failures. In 1975, Chinese seismologists successfully predicted the Haicheng earthquake based on foreshock activity, saving thousands of lives. It was heralded as a breakthrough. The following year, the Tangshan earthquake struck without warning, killing over 240,000 people. The lesson was brutal. Sometimes patterns appear before major earthquakes, sometimes they don't, and you can't tell which scenario you're in until after the fact. Italy learned this lesson the hard way in 2009, when 6 scientists were convicted of manslaughter for providing false reassurances before the L'Aquila earthquake. The convictions were later overturned, but the damage was done. Scientists became even more reluctant to make public statements about earthquake risk. The legal precedent sent a chilling message. You can be held responsible for what you say, but also for what you don't say. So what scientists do instead is monitor quietly and update internal assessments. They don't issue public predictions. They don't declare elevated risk windows. They just watch the data and wait. And right now, the data is showing some things that warrant closer watching. Stress transfer models suggest the January 14th earthquake may have increased stress on the segment of Cascadia directly adjacent to the rupture zone. Not by a lot, not enough to guarantee anything, but measurably. GPS networks show slight changes in ground deformation patterns along the Oregon coast. Again, nothing dramatic, just shifts that indicate the crust is adjusting. One GPS station near Newport, Oregon, moved 0.7 centimeters to the east in the 48 hours following the earthquake. That's less than half an inch. It sounds trivial, but GPS accuracy is now measured in millimeters. When a station that's been stable for years suddenly shifts, it means something changed in the stress field beneath it. The motion suggests compression, the coastal crust being squeezed slightly as the offshore rupture redistributed forces. Tidal stresses are approaching a peak. The new moon on February 8th will bring the strongest tidal forces of the month. Full moons and new moons are statistically correlated with slightly elevated earthquake rates, not because the moon's gravity is strong enough to trigger earthquakes, but because tidal stresses can act as a final nudge on faults that are already critically loaded. Research published in 2024 analyzed over 10,000 earthquakes globally and found a weak but statistically significant correlation between tidal peaks and earthquake occurrence for events larger than magnitude 5.5. The correlation isn't strong enough to predict specific earthquakes, but it suggests that tidal stress, while tiny compared to tectonic stress, can matter in systems that are already on the edge of failure. Geomagnetic activity is forecast to remain elevated through the end of January as Earth continues to rotate through the high-speed solar wind stream. The stream will persist for another week before diminishing. That's not a long window, but it's not negligible either. Space weather forecasters at NOAA are tracking a second coronal hole that will rotate into Earth-facing position around January 20th. If it produces another high-speed stream, geomagnetic activity could remain elevated into early February. That would overlap with the February 8th tidal peak, creating another convergence moment similar to January 14th. Add it all up, and you get a scenario where multiple small stressors are converging during a period when the crust is already adjusting from the January 14th event. Does that mean a magnitude 7.5 earthquake is imminent? No. Does it mean the probability is slightly higher than baseline? Maybe. Slightly. The honest answer is we don't know. And that uncertainty is what drives people to search for patterns, for signals, for anything that might provide advance warning. which is why some researchers are now paying attention to things happening far beyond Earth's immediate environment. Things that shouldn't matter, but might. On January 9th, 2026, astronomers using the Panoramic Survey Telescope and Rapid Response System in Hawaii detected an object moving through the outer solar system at a velocity that didn't quite make sense. The object, temporarily designated 3I/Atlas 01, was on a trajectory that suggested an interstellar origin, similar to Oumuamua in 2017 and Borisov in 2019. But unlike those previous visitors, this object was exhibiting behavior that challenged existing models. Interstellar objects are incredibly rare detections. Only 2 have been confirmed before this month. They matter because they're samples of material from other star systems, travelers from places we can't reach, carrying information about planetary formation in environments completely different from our own. When we spot one, we learn something about the universe beyond our solar neighborhood. The first interstellar visitor we confirmed, Oumuamua, sparked years of debate. Its elongated shape, unusual tumbling motion, and slight acceleration away from the sun defied easy categorization. Was it a comet? An asteroid? Something else entirely? The scientific community argued passionately about its nature, with hypotheses ranging from a nitrogen iceberg to, in more speculative corners, an artificial probe. Most researchers settled on exotic comet as the most likely explanation, but the object left our solar system before we could gather enough data to be certain. Borisov, the second confirmed interstellar object, was more conventional. It looked like a comet, behaved like a comet, and had a composition similar to comets in our own solar system. In some ways, Borisov was reassuring. It suggested that planetary formation across different star systems follows similar rules, produces similar objects, operates under similar physics. 3. I/Atlas 01 was unusual from the start. Its trajectory showed non-gravitational acceleration, meaning it was speeding up or changing direction in ways that couldn't be explained by the sun's gravity alone. This happened with Oumuamua too, and the most likely explanation is outgassing cometary jets of vaporized ice creating tiny thrust. But 3I was accelerating without showing any of the typical cometary signatures. No coma, no tail, no detectable water or carbon monoxide emissions. When comets approach the sun, solar heating vaporizes their ices, creating the characteristic coma and tail we associate with these objects. The vaporization is visible across multiple wavelengths. Infrared telescopes detect water molecules. Ultraviolet instruments pick up carbon monoxide and carbon dioxide. Radio telescopes can identify organic compounds. 3I showed none of this. It was accelerating like a comet, but looked like a rock. Spectroscopic analysis showed it was dark, extremely dark, reflecting less than 4% of the light hitting it. For comparison, charcoal reflects about 5%. This object was blacker than charcoal, and it was tumbling, rotating on multiple axes in a chaotic pattern that suggested either a very irregular shape or a recent collision. The darkest objects in our solar system are typically carbon-rich asteroids or comet nuclei covered in organic tholins, complex molecules created by radiation processing of simpler compounds. But even these objects rarely get below 5% reflectivity. 3I was darker. Spectra taken by the Very Large Telescope in Chile showed absorption features consistent with iron-nickel alloys mixed with silicate minerals, a composition more typical of differentiated planetary interiors than primitive asteroidal material. The astronomy community began intense observations. Telescopes in Chile, the Canary Islands, Arizona, all turned toward the object. Within 72 hours, researchers had accumulated enough data to propose a hypothesis. 3I might not be a simple rock or comet fragment. It could be a shattered piece of something larger, possibly a disrupted planetary core from another star system, material that had undergone differentiation and then catastrophic fragmentation. Planetary differentiation is the process by which heavier elements sink to the center of a forming world, while lighter materials float to the surface. Earth has an iron core surrounded by a silicate mantle because gravity sorted materials by density during our planet's molten youth. If 3I is indeed core material, it means it came from a world that formed, differentiated, and then was destroyed violently enough to scatter fragments across interstellar space. This would be extraordinary. We've never detected planetary core material from another star. If confirmed, it would tell us that planetary destruction, catastrophic collisions that completely disassemble worlds, happens elsewhere in the galaxy. It would give us a window into violent processes we've only theorized about. The implications extend beyond astronomy. If planets can be shattered, if worlds can be torn apart and scattered, then planetary systems are more fragile than we assumed. The solar system we inhabit, with its orderly arrangement of rocky inner planets and gas giants in stable outer orbits, might be an exception rather than the rule. Most planetary systems might go through chaotic phases where collisions reshape everything, where worlds are built and destroyed in cycles we're only beginning to understand. 3I's velocity was another puzzle. At 47 kilometers per second, relative to the local standard of rest, it was moving faster than most interstellar objects should be. That speed suggests it was ejected from its parent system with significant energy, possibly during a close stellar encounter or a supernova explosion. The object might have been wandering through the galaxy for millions of years, a fragment of a world that died when our own solar system was still young. But here's the part that matters for our story. The detection of 3I came at the same moment that Earth-based systems were showing unexpected behavior in multiple domains. The January 14th earthquake, axial seamounts inflation, elevated solar activity, and now, an anomalous object in space exhibiting physics we don't fully understand. Coincidence? Of course. These phenomena have nothing to do with each other causally. An interstellar object passing through the solar system doesn't affect tectonic plates or magma chambers or fault zones. The distances involved make any physical interaction impossible. But there's a pattern here worth noting. Multiple systems across multiple domains are showing behavior that deviates from baseline. Earth's crust is stressed, the sun is active, a volcano is inflating, and now space itself is delivering something we didn't expect. We're living through what scientists call a model-breaking era. Artificial intelligence is detecting patterns in data that human researchers missed. Machine learning algorithms are combing through astronomical surveys, identifying objects and phenomena that would have taken decades to find manually. Neural networks trained on seismic data are recognizing precursor signals invisible to conventional analysis. AI systems monitoring space weather are predicting solar events with accuracy that seemed impossible 5 years ago. Instruments are achieving precision that reveals phenomena we couldn't see before. Gravitational wave detectors can measure distortions in spacetime smaller than the diameter of a proton. Seismometer networks can track ground motion at the nanometer scale. Telescopes can image planets around other stars directly, resolving features we once thought would remain forever invisible. Old assumptions are being tested against new observations. And in multiple fields, geology, space weather, astronomy, solar physics, the models are straining. The standard model of solar activity, developed over decades of observation, predicts solar cycle behavior based on dynamo theory and magnetic field evolution. But the current solar cycle, cycle 25, is proving more active than predicted. The models said it would be weak. Instead, it's approaching the intensity of much stronger cycles. Something in our understanding of solar magnetic field generation is incomplete. Earthquake forecasting models rely on assumptions about stress accumulation rates, fault friction properties, and rupture mechanics. But recent large earthquakes keep surprising researchers by rupturing segments thought to be locked differently, or by propagating through barriers that models said should stop them. The 2011 Tohoku earthquake, the 2016 Kaikoura earthquake, and others have all challenged standard assumptions. Even our models of planetary formation are being revised. The discovery of hot Jupiters, gas giant planets orbiting closer to their stars than Mercury orbits our Sun, completely upended theories that said such configurations were impossible. The detection of planets around binary stars, rogue planets wandering through interstellar space, and now potentially shattered planetary cores all push us to expand our conception of how solar systems form and evolve. This isn't collapse, it's growth. Science advances by breaking old frameworks and building better ones. But the process is disorienting because it means admitting that what we thought we understood less well than we believed. The physicist Richard Feynman once said that science is the belief in the ignorance of experts. He meant that progress comes from questioning authority, from testing assumptions, from being willing to say, "We don't know," when the data doesn't fit the models. We're in one of those moments now, across multiple disciplines. 3. I/Atlas 01 will continue its journey through the solar system and eventually disappear back into interstellar space. It's not a threat. It's not a sign. It's just a visitor. A piece of cosmic debris reminding us that the universe is larger and stranger than our models predict. But its arrival during this particular moment feels symbolic. We're in a phase where prediction is failing, where certainty is elusive, where the things we count on to behave predictably, tectonic plates, the sun, orbiting objects, are all showing us that they contain more complexity than our equations capture. And that brings us to the only honest way to end this story. Here's what we know with confidence. Earth's crust is under stress. It's always under stress. But right now, the stress is distributed in ways that have some researchers paying closer attention. The Cascadia subduction zone is locked. It's been locked for over 3 centuries. It will unlock eventually. When it does, the resulting earthquake will be significant. The geological record is unambiguous on this point. Cascadia has ruptured repeatedly throughout its history. Turbidite deposits, layers of disturbed sediment on the ocean floor, mark at least 41 major earthquakes over the past 10,000 years. Coastal marshes along the Pacific Northwest preserve ghost forests, stands of trees killed when the land suddenly dropped during past megathrust events. Tsunami deposits in Japan provide independent confirmation of the timing and magnitude of these ruptures. This isn't speculation. It's documented history written in rock and sediment. The question has never been whether Cascadia will rupture again. The question is when. We know that axial seamount is inflating. It's done this before. It will erupt again. The instrumentation is giving us unprecedented data on how submarine volcanoes behave. We're learning things we've never known before. The Ocean Observatory's initiative has transformed our understanding of seafloor volcanic processes. Before the cable networks were installed, scientists could only visit axial occasionally, taking snapshots of its behavior during research cruises. Now they watch it continuously, tracking every earthquake, every centimeter of ground deformation, every change in hydrothermal vent temperature. The data is revealing patterns that would have been invisible with sporadic observations. One of the most surprising discoveries is how regular axial inflation cycles are. The volcano inflates at a remarkably consistent rate of about 60 centimeters per year. It's like watching a balloon being filled at a steady pace. When the inflation reaches a threshold, somewhere between 4 and 7 meters of uplift, the volcano erupts. The caldera floor drops as magma drains out. Then the inflation cycle begins again. This predictability is unusual for volcanoes. Most are chaotic systems with irregular eruption intervals. Axial's behavior suggests that its magma supply is stable and its plumbing system is well established. We're watching a machine that operates according to rules we're finally beginning to understand. We know that solar activity is elevated. The sun goes through cycles. It's approaching solar maximum in its current 11-year cycle. High-speed solar wind streams are normal during this phase. Geomagnetic storms are expected. None of this is unusual in the broader context of solar behavior. The sun has been cycling through activity levels for as long as we've been observing it. Galileo sketched sunspots in 1610. Astronomers have been counting them ever since. The 11-year cycle is one of the most reliable patterns in solar physics. We're currently in solar cycle 25, which began in December of 2019 and is expected to peak around 2025 or 2026. Every solar maximum brings increased sunspot numbers, more frequent solar flares, and higher rates of coronal mass ejections. Space weather becomes more active. Auroras become more common at lower latitudes. Satellite operators take precautions. Power grid managers prepare for potential disruptions. This is routine. It happens every 11 years. We've been through it before, and we'll go through it again. We know that an interstellar object is passing through the solar system, exhibiting properties we don't fully understand. This will lead to better models of planetary formation and destruction in other star systems. It's scientifically valuable and poses zero threat to Earth. 3I/Atlas 01 is currently beyond the orbit of Mars, heading outward toward the asteroid belt. Its trajectory will take it past Jupiter's orbit in about 8 months, then out into the outer solar system, and eventually back into interstellar space. It will never come close to Earth. It poses no collision risk. It's simply passing through, a messenger from another planetary system, giving us a glimpse of processes happening in distant parts of the galaxy. What we don't know is timing. We don't know if the January 14th earthquake was a pressure release or a stress transfer event. We don't know if axial will erupt in 6 months or 6 years. We don't know if geomagnetic activity has any influence whatsoever on earthquake timing. We don't know what 3I is made of or where it came from originally, and we definitely don't know if any of these phenomena are connected beyond the coincidence of occurring during the same general time frame. This is the uncomfortable truth that science often delivers. We have more questions than answers. We can measure things with extraordinary precision, but still struggle to predict outcomes. We can document patterns, but can't always explain mechanisms. The universe is revealing its complexity faster than we can build theories to explain it. Here's what you should not do. Don't panic. Don't interpret every subsequent earthquake as the beginning of the big one. Don't assume that increased solar activity means disaster. Don't read patterns into noise. Don't let uncertainty paralyze you into inaction or drive you toward irrational decisions. Panic is the enemy of rational thinking. When people panic, they make poor choices. They buy out stores of bottled water they don't need. They spread rumors that amplify fear. They ignore actual risks while obsessing over imaginary ones. Panic feels like action, but accomplishes nothing useful. Pattern recognition is one of humanity's greatest strengths. It's how we learn to anticipate seasons, predict animal migrations, and develop agriculture. But it's also a liability. We see patterns where none exist. We connect dots that shouldn't be connected. We remember hits and forget misses. This cognitive bias, called apophenia, makes us vulnerable to false correlations and spurious conclusions. 3 earthquakes in a week doesn't mean a bigger one is coming. It might mean nothing more than random fluctuations in a seismically active region. Higher solar activity coinciding with an earthquake doesn't establish causation. It might be pure chance, the kind of temporal overlap that happens constantly in a complex world. Here's what you should do. If you live in the Pacific Northwest, have an earthquake preparedness plan. You should have had one already, but if you don't, now is a good time. Know where your emergency supplies are. Know how to shut off gas lines. Know your evacuation routes if you're in a tsunami zone. This isn't fear-based preparation. It's rational acknowledgement that you live in an active seismic region. Preparedness doesn't require belief in imminent disaster. It requires acknowledgement of possibility. You don't need to think an earthquake is coming next week to justify having water, food, medical supplies, and a plan. You just need to recognize that you live in a place where earthquakes happen and being ready is sensible. The same logic applies to other natural hazards. If you live in tornado country, you should know where your shelter is. If you live in hurricane zones, you should have evacuation plans. If you live in wildfire territory, you should have defensible space around your home. These aren't paranoid overreactions. They're rational responses to known risks. Follow credible sources. The United States Geological Survey, the National Oceanic and Atmospheric Administration, university research institutions. These organizations will provide information as it becomes available. They won't speculate. They won't sensationalize. They'll give you data and context. The information ecosystem is polluted with bad actors who profit from fear. YouTube channels with alarming thumbnails. Social media accounts sharing cherry-picked data. Websites selling survival gear alongside earthquake predictions. These sources have incentives to make you afraid because fear drives clicks, shares, and purchases. Credible scientific institutions have different incentives. Their reputation depends on accuracy. Their funding depends on producing reliable knowledge. They're conservative by nature, sometimes frustratingly so, but that conservatism exists for good reasons. When the USGS says something, you can trust they've checked their data and consulted their experts. Understand probability. A slightly elevated risk is still a small risk. Most elevated risk windows pass without incident. But most is not all. Preparedness is about being ready for low probability, high consequence events. This is where humans struggle. We're terrible at evaluating tail risks, those unlikely but catastrophic outcomes that hide at the edges of probability distributions. We underestimate them, treating low probability as equivalent to impossibility. Then, when they occur, we're shocked, as if no one could have seen it coming. The 2008 financial crisis was a tail risk. The Fukushima disaster was a tail risk. The COVID-19 pandemic was a tail risk. In each case, experts had warned about the possibility. In each case, societies were underprepared because low probability felt like no probability. And here's the philosophical part, the part where we zoom out and think about what all of this means. Earth is not a static ball of rock. It's a dynamic system that's been adjusting for 4.5 billion years. Plates move, volcanoes erupt, the magnetic field flips, ice ages come and go. Mass extinctions reset the evolutionary clock. The planet doesn't care about human timescales or human preferences. It operates on its own schedule. The geological timescale is humbling. Mountains rise and erode. Oceans open and close. Continents collide and split apart. Species emerge, flourish, and go extinct. All of this happens on timescales that dwarf human lifespans and human civilizations. We've been watching Earth carefully for maybe 2 centuries, using instruments that can measure tiny changes in ground position, magnetic field strength, seismic wave propagation. Before that, we have historical records going back a few thousand years. Before that, geological evidence that we're still learning to interpret. In the context of 4.5 billion years, our observations cover essentially zero time. We're watching a movie that's been playing for eons, and we showed up for the last fraction of a second. Drawing conclusions about long-term behavior from such limited sampling is risky. We're living through an adjustment phase. Maybe a small one. Maybe the beginning of something larger. We won't know until after it's happened. And that's uncomfortable because humans crave certainty. We want to know what's coming. We want to prepare for specific scenarios. We want someone to tell us exactly what will happen and when. But the universe doesn't work that way. Complex systems don't announce their transitions in advance. They shift. They reorganize. They find new equilibrium states. And sometimes those shifts are dramatic. The only certainty we have is that change is constant. Earth will continue adjusting. The sun will continue cycling through active and quiet periods. Objects will continue falling through space. Volcanoes will continue erupting. Earthquakes will continue happening. Life will adapt, as it always has, to whatever conditions emerge. The planet isn't panicking. It's not frightened. It's not counting down to disaster. It's adjusting, the way complex systems always adjust when multiple variables shift simultaneously. We should approach this the same way, not with fear, not with denial, but with informed awareness, watching the data, updating our understanding as new information arrives, preparing reasonably for possibilities without obsessing over timelines we can't predict. Because adjustment phases are when history quietly changes direction. Not with announcements, not with warnings, just with the patient, inexorable movement of forces too large to stop and too complex to fully predict. The earthquake off Oregon happened. Axial is inflating, the sun is active, an interstellar visitor is passing through. These are facts. What they mean, collectively, is still being written, and you're living through the chapter where we find out.